So in the previous videos about limits, we kind of went through all the definitions of the rules for calculating limits, and we looked at various examples that concentrated on different types of functions. In this video, we will focus on how limits are used in other areas of math, and specifically we'll look at the two-circle and a limit problem. This is a problem that math teachers really like because it includes a limit question, it includes some geometry. When you solve it, it can include either trigonometry or algebra. So it's a great question for combining different topics in mathematics. And this is a question that you will see in various calculus textbooks, on exams, and so on. It's a little bit more advanced than the examples we did in the previous videos, but we'll go through it slowly. So what is the two-circle limit problem? It starts off with two circles. There's a stationary circle or a constant circle that is centered at the point R and 0, so on the x-axis here, and its radius is also r. It will touch the y-axis at x equals 0 and y equals 0, and it'll go farthest on the x-axis to 2r. So that is our first circle. Then we have a shrinking circle with radius r, so it has a variable radius r. It is centered at the origin. The origin is the point 0, 0, and it's varying in that the radius can change. So our small r here is a varying variable. And the two circles will cross each other at a certain point. They'll cross right here at B. And we'll take the point A, which is where the varying circle cuts into the y-axis. So this point A here, we will connect it with point B, which is where both circles cross in the upper right quadrant. And then we take that line that connects A and B, and we draw it all the way down to the x-axis, and we find a new point L, which is where the line crosses the x-axis. And typically the question is, what happens to L? So if we change R, how does L change? And why is this interesting? Well, we can expect that as R goes to 0, right, as this smaller variable circle gets closer and closer to 0, our L point will go farther and farther down the x-axis. So sort of intuitively, it looks like L will become larger and larger as R becomes smaller. Maybe we'll even go to infinity. And so that is the big question. What happens to L, the limit of L, as R goes to 0? What does that equal? And I'll start off by saying that counterintuitively, it actually will not go to infinity. We will find that it actually has a finite limit. But in order to do so, we have to kind of do a little bit of math to see what L is as a function of R, and then take the limit. And in order to do that, there are various approaches. There's a trigonometric approach, there's an algebraic approach, and there's sort of a more geometric, simple approach. We will leave the trigonometric approach to a different video since we haven't gone over trigonometry together yet. But in this video, I will show the two other approaches. So the first step in analyzing this is to figure out what B is, right? We have to know what this point is in order to know what the line is, what our A to B line looks like. And so how do we find B? Well, let's write B as being point on the xy coordinate system, so it'll have an x and a y. And how do we find the x and y? Well, we know that this point at B is on both circles. It's on the small circle and on the large circle. So let's write out the equations for these two circles. So the first circle is centered around the origin. The origin is x equals 0 and y equals 0. And so the formula for that circle is just x squared plus y squared equals our little r squared. This is just the formula for a general circle centered at the axis origin. What is the formula for the larger r circle? Well, here we have something a little more complicated. We are centered around the point capital R and 0. So we have x minus capital R squared plus y squared equals capital R squared. Let's simplify this lower equation. Let's open the parentheses. We get x squared minus 2xr, this is binomial, plus r squared equals plus y squared equals r squared. So we can cancel the two r squareds from both sides, and we remain with x squared plus y squared, and I'm going to move the 2xr to the other side of the equation. So now we have a similar form for these two equations, and we can use that similar form. We can write that x squared plus y squared equals 2xr, but it also equals lowercase r squared, right, from this equation. Okay, so let's move this up a little bit. So now what we find is that x of this point B is equal to r squared over 2 capital R. So this is a general formula for the x value of the point where the two circles intersect. What is our y value? Well, we can use this equation here to find our y value. We know that y squared will be equal to r squared minus x squared, because we moved the x squared to the other side of the equation. So y squared equals just r squared minus r to the power 4 divided by 4 capital R squared. Why is that? Because we're squaring the value of x, so we get in the numerator r to the power of 4, and in the denominator we just get 2 squared, which is 4, times capital R squared. Let's simplify this a little bit. We'll write it as r squared times 1 minus r squared divided by 4 capital R squared. So we've just taken r squared out of the parentheses. We've simplified it a little bit. Okay, so now we have our y squared, and if we want it in terms of y equals r. We're taking a square root of 1 minus r squared divided by 4 capital R squared. Okay. Obviously, this formula now is only correct for situations where lowercase r is less or equal to 4 capital R squared. So we can't go to very, very large r's. We'll get the square root of something negative. So we have to have r squared divided by 4 capital R squared less than 1 in order for this to hold. Okay, so we have our x and our y, and we can write them out a little more neatly. We can write it as xy equals r squared divided by 2r 2 capital R, and R times square root of 1 minus R squared divided by 4 capital R squared. And this result kind of makes sense in terms of the units. We can see that we have R squared divided by R, so that's 1 unit of length. And then we have here R, in the Y section we have R, and this is a unitless number here because we have R squared divided by capital R squared. So we got our X and Y, and we can use these to start solving for L. So as a reminder, we found this point here, B, and we have the point A, and we know that A and B are on the same line that eventually crosses the x-axis at the point L0. Okay. So now that we have the coordinates of this point B, where the two circles intersect, we can now try to think about how we will figure out what L equals to. How do we do that? Well, we're going to look in slightly more detail on a kind of geometric solution, and I'll also hint at the more algebraic steps to take. So let's draw a little bit of a close-up of this problem without the circles. So we have a point A and we have a point B, and we know that they connect, and then their intersection is what we're interested in, the intersection with the x-axis here. Okay, so we now know the point A, which we said is 0 and lowercase r, right? And we have the point B, which we wrote as x and y, and we have their details up here. Right. Okay, so now if we look at the point B, let's pass a parallel line through B and the y-axis parallel to the x-axis. So basically we're taking the point B and drawing a line that is perpendicular to the y-axis, and this line now is similar to the x-axis in that it's parallel to it, right? It's basically a parallel line from B to the y-axis. Now this line and this line that we've been looking at all this time form an angle, this angle here. And this angle, let's call it alpha. The angle alpha is equal to the angle between the line and the x-axis. Why is that? These are what we call corresponding angles between two parallel lines. So they're corresponding because the x-axis and this line between B and the y-axis are parallel, and there's a straight line that intersects these two parallel lines. So alpha here is the same as the angle here, so we can call it alpha. Okay, so we have two equal corresponding angles, and we can now look at some of this angle's properties, and specifically it's convenient to look at the tangent of alpha. What is the tangent equal to? Since these are basically 90-degree triangles, right? The x-axis and the y-axis form a 90-degree angle, as does this parallel line to the x-axis. And so what is the tangent of alpha? The tangent of alpha is given by this side, right, which is basically our y at point A, divided by this side, which is just given by L. We can also write the tangent of alpha as this little area here. What is this little area here? It's just the y value at A minus the y value at b, because this is perpendicular here, right? So it's r minus y, divide by this length here. This length here is just the x value at the point B, so it's r minus y divided by x. And since this angle is the same angle, we can say that these two ratios are equal. So we get r divided by L is equal to r minus y divided by x. Okay, so we have an equation that combines L with r, y, and x. And we know that y and x are functions of lowercase r and uppercase R, so we might actually have an equation that'll help us solve this. Let's simplify this. We'll multiply both sides by L. So we have r equals L times r minus y divided by x. Let's multiply by x divided by r minus y so that we get r times x divided by r minus y equals L. Okay, so we have to simplify now this term, and we will use the values we found for x and y up here. So bear with me. Let's write this out. We'll write it. We'll change sides. L equals R. Okay, what is our x? Our x is just r squared divided by 2 capital R times, I'll write this as a separate ratio, r minus y. So we have r minus, our y was just r times the square root of 1 minus lowercase r squared divided by 4 uppercase r squared. Okay, so we found our formula for L, and we can now start playing with this a little bit. Let's see what we can do with this. Okay, so let's first take this r out of the parentheses. Simplify this as r times r squared divided by 2 capital R, 1 over r times 1 minus square root of 1 minus lowercase r squared divided by 4 uppercase r squared. Okay, so first we can cancel this lowercase r here, and we remain with a term that includes in the denominator this square root. Now, if we at first look at it, we could say, oh, if we're looking at the limit of L as r goes to 0, well, when r goes to 0, L will go to 0 too, because we're multiplying by r squared. But if we look at this term in the denominator, what happens when r goes to 0? Well, we get the square root of 1. Square root of 1 is 1, and so we get 1 minus 1, which is 0. So we would basically be saying that it goes like 0 divided by 0, which is not a legal set of operations. So we have to simplify this further in order to see whether we can take that limit in a more correct way. So obviously separating these two parts of the function, this part and this part, into two separate limits is not okay. We cannot use that rule. But in a previous video, we did look at something similar. And we used the fact that when we have a minus b times a plus b, we get a squared. This is equal to a squared minus b squared. So here we have 1 minus the square root of something. If we want to get rid of this square root, we can multiply the denominator by 1 plus the square root. Of course, we cannot just multiply the denominator. We will have to multiply also the numerator. So let's do that. We'll write L equals lowercase r squared divided by 2r. Now we're going to multiply the numerator by 1 plus the square root of 1 minus r squared divided by 4r uppercase r squared. We'll divide this by 1 minus the square root, I'm not going to write what it's inside because we're going to simplify this further, times 1 plus the square root, right? And we know what's inside the square root. Okay, and when we multiply the 1 minus and the 1 plus, we reach something that is a little simpler. What's in the numerator stays the same. But in the denominator now we have 1 minus. We have 1 minus what's inside the square root without the square root. So we have 1 minus lowercase square root r squared divided by 4 uppercase square root squared r. Okay. Now when we take 1 minus 1 here, these cancel and we're left with a positive term here. We're left with r squared divided by 2r, and here we have r squared divided by 4 capital R squared, all this in our denominator, times 1 plus that square root. Okay, and we've seen it enough times so that I don't have to copy it every time. Okay, so now let's look at this again. We have L equals r squared divided by 2 capital R lowercase r squared. And now this 4r squared, because it's the denominator of the denominator, it will go up to the numerator. And we can use our usual rules to simplify. And so this term is just 2r. And then we have 1 plus the square root of 1 minus lowercase r squared divided by 4 uppercase squared. Okay, now we can take the limit of this function. So now we can look at the limit of L as lowercase r goes to 0. That is just the limit, r goes to 0, of 2r times 1 plus the square root of that term. Okay, now what happens when r goes to 0? Well, now we have a simple limit. This term will go to 0, and so we'll be left with a 1 here in the square root. 1 plus 1, that's 2, so we'll be left with 4 uppercase R. And that is our result. So when r goes to 0, L equals 4 times the radius of our stationary circle. And if we want to find out what happens if r equals 3, then our limit when r goes to 0 of L is just equal to 12, and so on. We can do this for any, basically for any stationary circle. So this was the full-blown detailed solution when we used an angle considerations or sort of geometry. We also used trigonometry a little bit, although really we could just say that these were similar triangles and therefore the ratio of the sides should be equal. So this trigonometric solution is really a geometric one where we used similar angles which led to similar triangles and therefore equal side ratios. So the sides are not equal, but the ratios are equal. So that's basically how we did this, and we used the tangent to basically define that ratio. So that ratio was the tangent. But even without knowing what a tangent did, we could solve this problem this way. There's one other solution that I would like to show. I will not go through the details because it's really very similar, but this one might be a little bit more intuitive to those of you for whom geometry is less of an intuitive tool. And in this case, what we would do is sort of similar. We have our point A, we have our point B. We put a line through them and we continued it to its cross section, and we're interested in finding L, right? And so using A and B, which we found out, right? B is xy, and we found out what xy is, and A is just 0 and r. We can use these 2 points to define a line. How do we do that? We find the slope. The slope is just given by y minus r divided by x minus 0. So we use that to define our slope. And I will not go into the detail, but if you do, you can find that the slope is just minus 2 uppercase R divided by R times 1 minus that famous square root we have of 1 minus lowercase r squared divided by 4r squared. So if you go through the algebra of this, now that we have x and y, you can figure this out. Okay, so you get the slope, and then we know that the constant of the line of straight line is just equal to lowercase r, because the constant is given by y of x equals 0, and that in this case is just this point, which is the upper point of the highest point of the lowercase r circle. So our constant is r, our slope is this slope, and so we can write out that y equals minus 2r over lowercase r, 1 minus the square root of 1 minus r squared divided by 4 uppercase r squared times x plus lowercase r. And the intersection is given by the condition that y equals 0. So we will write 0 equals minus 2r over lowercase r, 1 minus square roots, times, instead of x, we're going to write L, because we're going to try to figure that out, plus r. And then we can solve for L using the values that we have here, and we will end up with the same type of limit, the same problem, where we can't separate the two parts of a function and look at the separate limits. We actually have to simplify the function so we get to a point where we can take the limit, and you'll see that you will get the same, basically the same value, that L equals 4 times R for any uppercase. So this was a considerably longer video, but it did give the very detailed solution of a problem that does repeat itself in calculus classes. You will see this problem with various values of R, and so it's a good problem to know in detail how to solve. There are other solutions that make use of trigonometric equalities and identities, and if trigonometry is your strong tool, then I would suggest trying to solve it in this way, or looking up a solution. There are other solutions online that can help you with that approach. So thanks for joining me on this longer video, and I hope it was helpful.